And you remember that when we are dealing with things moving, we are only worrying about moving in one of the ways that we... Oh, sorry, I've just rubbed off mid. Monday 2 is a lesson with the other group. A number of them are out doing another exam, so I have said I'll do that as a revision lesson. By that idea, I'm not going to teach anything, but they can come and do revision, and I will go around and help them when they get stuck. You're very welcome to come along if you are not in a lesson. I do not give you permission to bunk off other lessons, okay? And then Wednesday 2, which is just before the exam, I've got the other group again, and you're very welcome to come along to that if you are available for the same reason. I'm not going to be teaching, so I don't want you to think they're getting extra help. They're not. It's just those are just opportunities for you to come along and do some revision. And yeah, right. So we've got to remember when we are dealing with things moving, we need to use a combination of Newton's second law, F equals ma. But that's only in one direction. So in this case, that's going to be when we resolve parallel with the slope, because we'll have equilibrium when we resolve perpendicular to the slope. And of course, we'll also have a bit of Suvat action in there as well, because in the direction in which it's moving, it's going to be accelerating at a constant rate. So the Suvat equations will be valid. So I really like these questions because there's no sort of set way of doing it. You've just got to, this is real Batman utility belt territory. You've got to really decide, you know, which is the technique which is going to work. So go on, have a go at drawing the diagram, and in a minute I'll go through where I would start. First question you should always ask yourself is which way does it want to go, or which way in this case is it going, and therefore friction is going to be in the opposite direction. If you're ahead of them and you want to ask for help on a particular question, please do. Don't suffer in silence. Remember, if it's already moving, friction is at its maximum limiting value, which is mu 0.4 in this case, times the reaction force. Suvat equations are in the formula book. I have a spare on page 8. I mean, I'm sure they'll be in the book somewhere as well. decided, and it doesn't matter if you do it the other way around, I've decided because it's sliding down the slope, I'm going to call that positive. So when I do my resolving parallel with the slope, I did the downhill force, which is 1 times g cos 40, g equals 40, take away the uphill, which is friction, equals 1 times a. If you did it the other way around, you'll just get a negative acceleration, which is fine, just means it's going in the opposite direction. But start off by working out A. G is not a variable, G is 9.8, so we know what that is. Sorry, it's not a variable on Earth. G does vary, but on Earth it's 9.8, and I know even then it does vary a bit. So I've worked out A, and I love the way this works because you have to combine both the resolving equations. Normally they're separate, but friction brings them together, doesn't it? So friction is a force that we consider when we're resolving parallel with the slope, but we can work it out from our perpendicular to the slope calculation because F is equal to mu times R. So I like the way that F sort of, brings it all together. So having worked out what F is, I can plug that in, get my value of A, and now I'm into good old-fashioned SUVAT. And the fact it's on a slope doesn't matter. It's still, S is 2 meters. We'll ignore the dimensions of the block. We'll assume that from there to there is 2 meters. So 2 meters. I know it starts from 0, because it says if the block is released from rest, so its initial velocity is 0, and I want to know t, so the formula you need is that one, but u is 0, so it becomes instantly a whole lot easier. I'll leave you to finish that one off. Please move on to number 7 if you're ready, and 8, 9, 10, as some of you I know will be, and please ask for help if you get stuck. We're not going to spend the whole lesson doing this because I want to move on to the next step. So what age do you think they're going to stop doing that? But I have a feeling I'm going to bump into them on the high street in 5 years' time and they'll still be doing, "Oi, Cooper!" Oh my God. So I get 8955, which rounds to 896 for my time. 896 seconds. So please say if you weren't able to get that. So it was, UT was nothing because the initial velocity was 0 at rest, starts from 0. So you're just left with this, a half times a times t squared. So you do 2 divided by a half and divided by 9.8, that's t squared, square root it. Bob is your uncle. I hope you fast forward these with the quiet bits, Lily, and anyone else watching. But still do the sums. So I'm going to do number 7, and then we'll move on. So as always, there's a sort of expectation that you're going to do as much practice in addition to that you feel you need to, which may be nothing and may be plenty. I'll leave you to decide.
I like a machine gun to use this.
So this one is the same three things, isn't it? Unified by, I should perhaps say, add that to the list, isn't it? So it's the same three things, resolving parallel to the slope, perpendicular to the slope, and SUVAT, but a different order here, because I'm going to start by using SUVAT to work out A. I can work that out because I know that it's released from rest. So initial velocity was 0. It travels half a metre in the first 2 seconds. So I can use good old S equals ut plus a half at squared again to work out A. I can then plug that into this formula to work out F. I'll know R, so I can work out mu. Yeah?
You're going to get the wrong answer because you've got cos 60 to 62.
Thank you. Thank you very much.
That was awful. I don't know why I phrased it like that.
You're going to get the wrong answer.
Because I had a few whispers going around the class.
I'm very, very regularly.
Did you?
I have this picture that in every other class, every other teacher school never makes a mistake, and
that is great.
I try. I do try hard. I could make up some sort of nonsense that I'm trying to empathise with you and your struggles, but no, it's just getting old. So I'm going to spend give you another 2 minutes to finish that off, and then I'm going to stop. So you might want to just, if you're ahead of me, consider that. And can I help anyone at all? The answers are quite good, aren't they? In that they do show you a method of sorts. So no. Always a relief when I get a number. Yeah. So, SUVAT told me that A was a quarter. Plugging that into this formula, 2/4 is a half. So I added F to both sides and took away a half. So I got my value of F, which I stored. Didn't really bother doing anything with it, but that was 2G cos 62 minus a half. I got my value of R, which I stored, And because F is equal to mu r, that means mu is F divided by r, which I worked out, and I got 0.5028, so 0.503. It's a coefficient, no units for the coefficient of friction. It's just a multiplier. It's not a, it doesn't have a unit. So you've got other questions there which are worth doing if you feel like you want to, and over the page it carries on, but it's more of the same really. It's all very similar, and the reason I feel relaxed to not spend hours practicing it is actually as we move through mechanics we're repeating the same thing, we're just making it a bit more difficult, so the difficulty is going to come anyway. So I want to move on, and I want to talk now about connected particles with slopes and friction. Before we do that, let me just remind you about where we've met connected particles before. I know for a fact that you'll all be very comfortable with this because it was one of the things that we revised ahead of the mock. I did have a copy of it open. There we go. Right. So this isn't in your book. This is in the Year 1 version of the book. So do you remember connected particles in Year 1? So it was pulleys or things towing trailers along a road. So should we have a look at question 2 here and just remind ourselves about how we approach this? It's very similar in a way to what we've just been doing because it's a combination of F equals ma and suvat. No friction because we're told that the pulley or the peg is smooth. Inextensible rope, which if you remember tells us two very important things. It means the tensions are the same and the accelerations are the same for both particles, because the way we approach this is we just deal with it as as two separate things. So we basically consider A and B separately. So I'm going to consider A and B separately. So for A, that's all I've got. And for B, that's all I've got. Except it's moving. So we're not balanced, it's moving. And I know that mass M is less than 35, so that tells me which way it's moving. I know that this is moving down, so it's accelerating in that direction. So that means this is going to be moving up. But these T's are going to be the same, and these A's are going to be the same. And it may be that suvat is going to help me calculate A because of what we're told here. So we're going to resolve vertically in both cases, and I'm going to consider that to be positive and that to be positive, so that I'm not having to deal with any negative accelerations. Don't have to do that. And then I'm going to use suvat to work out the acceleration, and it should all be well. So just see if you can remind yourself about how to approach those problems. It's another combination of the two techniques, Newton's second law if it was MA, and suvat. And we're actually asked to find acceleration, tension, and I was to find the tension at n, but you need to find the acceleration first. Acceleration isn't 9.8 because it's not falling freely. So I get A is 2.5, which I can then substitute into both of my resolving equations. I've tried to make it easy on myself by making down positive here and up positive there. That potentially is confusing, but I just want acceleration to be positive. So I get 35 times 100. That's in newtons. That's in kilograms. Just let's make sure I've got that right. So 8.3. Yeah, I'm sure. Okay, so that was year 1. And so what does year 2 bring? Well, this actually comes from the textbook we're using, but I've snipped it because it's just a bit off-putting with the example because it's got the work solution underneath it. I think it might be helpful for you to have a go at it without. So here is a connected particles problem from year 2. We're still going to solve it by breaking it into 2 separate problems. So it's still A and B. So A is something moving on a horizontal platform and it's got friction pulling it back. It's got the tension in the rope or the string pulling it forward, and there's an additional force holding it back of 15 newtons. But it is accelerating because it says that B falls to the ground. So there is an acceleration in that direction. B is going to be just the same as before. I've got the tension in the rope holding it up, 10G pulling it down, and we're told it falls. So there is an acceleration in that direction. And so it's still going to be F equals ma and suvat. We've got the added situation that in this side of things we'll have equilibrium when we resolve vertically, and we need to resolve vertically because that's how we work out F. But it's still the same thing, a mixture of those 4 things. We're going to, in this direction, resolve both vertically and horizontally. In this direction, we're only going to resolve vertically. And I'm going to do a bit of suvat as well, because of what it tells me about B. And I don't know which of those I need to do first. So, have a go. We're asked initially to find D. There's quite a lot of missing letters, but you should be able to slowly piece it together until you get two equations with two missing variables, and then it just becomes a bit of simultaneous equation action. And as I said, I nearly always with these either rewrite one or both as t equals or f equals or d equals, and then either substitute it or make them both equal to each other.
So it's still in maths at the moment. People are thinking about something difficult. This is the
So the way I've approached this one is I've taken this equation and written it as t equals. I know f. I've got f down here. That's stored on my calculator. It's pretty much exactly 23, but I'm going to use the stored value. I can work out a t equals equation from there. Remember, I'm after d, but I know d is equal to 2a. I got that from Suvat. So what I can now do is, because I've got both equations saying t equals, I can just say, right, and I'm going to get the A from this. So A is my only thing I don't know now. G is 9.8, F I've got stored on my calculator. So if I add 10A to both sides and take all that away, I get gives me what A is, and then D is double that. Okay. One thing I should say, store A before you double it to get D. And if you haven't, divide D by 2 and what have I done? Excellent. Right, so for D you should get 8.77. And that's a distance, so that's in metres, 8.77 metres. So if we look at the second part of this question, when B hits the ground, and the diagram is misleading because I've taken this from the second part of the question. It's on page, if you want to look at it, it's on page 132 and 133. It says B hits the ground. How long does it take A to stop? And it makes a specific point of saying A doesn't hit the pulley. So the diagram is misleading. But the 15 Newton force remains. So when B hits the ground, this diagram changes because the string goes loose, goes slack. So there's no longer any force there. This is now no longer an issue. And that means the acceleration is going to change because the forces have changed. In fact, it's going to slow down. We're told that because we're asked how long it takes to stop. So there's going to be an acceleration now in this direction. And that's obvious, isn't it? Because the only forces acting on that particle are now forces pulling it this way. So we're asked, how long does it take to stop? Could someone suggest what I need to work out before I can do anything else in this problem?
The acceleration?
Well, I do need to work out the acceleration, but before I do that even, I need to work out how fast it's travelling to start with. This is a two-part story, isn't it? Part one, the ball falls to earth. And part two, A keeps on moving after the ball's fallen to earth. So what I need to do, in order now I'm in part two, in order to use SUVAT, I need to know how fast it's travelling to start with at the beginning of part two. And that means I need to work out how fast it was travelling at the end of part one. So I'm going to now for B, say, right, how fast was B travelling at the end of part one? It started from rest. The distance it fell, I now know, it's 8.77, exact value stored hopefully. The acceleration was 4.385, exact value stored hopefully. I want to know how fast was it travelling at the end of that. So this is in part one. As B falls to earth, how fast is it travelling when it hits the ground? Because that's then going to be, in part two, how fast A is travelling at the beginning of that story.
How many marks is this?
Well, it's a long example question, so it would be a lot of marks, wouldn't it? So, can I get you, and I want you to have a go at this one before I see you tomorrow, can I get you to see if you can, for B, in part one of the story, work out how fast it was travelling when it hit the ground, all right? we can use that's the formula we use. That then becomes u, the initial velocity of this, in part 2 of the story. And I'm going to resolve in the same way as I resolved before to work out the acceleration and therefore work out how long it takes to stop. So if you, I mean, I'm saying finish this one off. It's on page 132 and 133 of the book, so you'll hopefully be able to check your answer or use the example, worked example to help you. But see if you can get somewhere with that between now and the start of the next lesson. And that means we can move on to some practice of this and some different sorts of connected particle problems next lesson. Lovely.